Hello, everyone. We'll get started in just a moment here. Welcome to those of you just joining us. We'll get the webinar started in a moment here. All right, hello and welcome to the first in this two-part webinar series that EERI is delighted to be presenting with our colleagues from the U.S. Geological Survey. My name is Elizabeth Angel. I'm the Communications and Program Manager here at EERI. And before we get going, I wanted to just take a brief moment for those of you who may not be familiar with us to talk about our organization and what we do. The Earthquake Engineering Research Institute is the leading nonprofit organization that brings together professionals from a wide range of disciplines and backgrounds who share the common goal of better understanding earthquake risk around the world and increasing earthquake resilience in our communities. You can find out more at our website, and we encourage you to join us if you share this mission and are interested in our opportunities to network, to learn, and be part of this effort. I wanted to also acknowledge that this webinar series is made possible by funding and support from the Federal Emergency Management Agency, by our Learning from Earthquakes Endowment Fund, and by many EERI members. So thank you for making these events possible. I also want to acknowledge and thank our subscribing members who provide institutional support to EERI that helps us put together educational programs like these, particularly Computers and Structures, Inc., and the other subscribing members on this page and this one. So thank you to all of them for your support. Finally, I'll share a link in the chat, but I just wanted to mention some upcoming webinars we have. First, next week, same time slot, the second webinar in this series, which will focus on the engineering and building code applications of the seismic hazard model. So we encourage you to attend. And if you were registered for today's webinar, you're also registered automatically for that one. So you should just be able to join from the same link, or the link that will be emailed to you. And then we also have a quick quake briefing webinar coming up, organized with our Northern California regional chapter, which will also feature a couple of great folks from the USGS. And that one's going to focus on the recent earthquake swarms in Southern California, and particularly on Shake Alert and its use in those. So I'll put a link to our upcoming events page where you can look at more and register for those in the chat later. And on that note, I'd like to turn it over to our moderator today, Jack Baker, Professor of Civil Environmental Engineering at Stanford University and editor-in-chief of our journal Earthquake Spectra, who's going to talk about the special collection that for the seismic hazard model papers that we'll be discussing today. Jack, go ahead.
Great, thank you. And thanks everybody for joining today. It's great to see a big attendance number here and reflecting the very large interest in this project that I know we've seen from many communities. So I'm here kind of as a representative of Earthquake Spectra, EERI's academic journal. And this webinar is kind of connected to a special collection that the journal has published that documents many of the papers, academic papers related to this project. And so you'll get a link to that special collection in the chat if you don't have awareness of it already. We'd encourage you to go take a look at the papers in detail. But this webinar is a great chance to hear from several of the leaders of that project about the high-level concepts and developments that were undertaken with the project. And I'll note that, as Elizabeth said a bit, EERI, its mission and core values, and connected to that, its journal, Earthquake Spectra, we note some key values of understanding earthquake risk and increasing resilience. And the first core value listed on the organization's webpage is to be working at the interface of research and practice. And I think this USGS project and the partnership between the USGS and the EERI related to hazard characterization is a great example of ways that the Institute wants to contribute to understanding earthquake risk. And we're really pleased that the USGS was willing and able to partner with us on helping publish and review this work as part of their general dissemination work. So with that, maybe we can turn to a couple notes about today's speakers. So we're fortunate to have 4 of the leaders of various parts of this large project that was contributed to by many more scientists and engineers as well, as I think you'll probably hear in the presentations. So we'll get a chance to step through some of the kind of an overview of the project and results, as well as kind of some key components and products related to this very large and complex project as well. Let's see, I guess it was on the previous slide, but just one more reminder is as you're listening to these presentations, we'll have a chance to have some discussion. So note any of your questions in the Q&A box, not the chat box. That Q&A queue can fill up over the course of the presentations, and then at the end, we will go through those and have some discussion about kind of common questions and things that come up. But you don't need to hold your questions until the end for the Q&A session. They'll stay preserved until we have a chance to address them. So I'd love to hear your thoughts and areas where you'd like to have some discussion or further clarification. Okay, so with that, I think we can transition to our first speaker. So Allison Shumway, who's a research geophysicist at the U.S. Geological Survey, is going to be providing an overview and related to some updates of the 2023 publication of the National Seismic Hazard Model. So Allison, thanks for being here, and we look forward to hearing from you.
Great, thanks, Jack, and thanks, EERI. Yeah, and I just want to mention, Mark Peterson was originally supposed to be giving this presentation, and he just wanted to send his apologies for not being able to be here today. So I will be representing the NSHM project. And I'm going to give an overview of our 2023 50-state NSHM and some of the revisions we've made since the release last December. Okay, so in December 2023, the USGS released the first 50-state NSHM since 2000 in earthquake spectra. This was a multi-year effort with additional funding from Congress. Over 100 expert scientists and engineers contributed to or reviewed the NSHM, as could be seen by the 54 co-authors on the paper, 6 review panels that reviewed the model, and then 23 public workshops that we had over the course of Hawaii, Alaska, and the conterminous US. Since then, the NSHM has been revised. It's been reviewed by our steering committee, and it's been recommended for publication by Earthquake Spectra, and is currently under consideration for implementation in building codes and other hazard and risk assessment projects. So the original 2023 50-state NSHM, which I'm just going to give a general overview because Ned's going to be talking more about the ERF parameters that went into the model, and Morgan will be talking about the ground motion characterization. But we've added 360 additional faults. There was implementation of fault-based deformation models that included geologic and joint geologic and geodetic information. We introduced new declustering and smoothing algorithms. We used new magnitude area relationships. We used inversion-based methodology for inclusion of multi-fault ruptures in the Western US, and this allowed us to include a wider range of epistemic uncertainties. We updated the structural and segmentation model for the Alaska Aleutian subduction zone. And then for Hawaii, we used a rate model that was based on 3 temporary varying 6-year time periods. On the ground motion characterization side of things, we included new semi-empirical NGA subduction ground motion models. We adjusted the NGA East ground motion models to reduce biases seen when we compared these with regional records. We used new 3D ground motion simulations for Seattle and Los Angeles regions. We either updated or added new basin depth amplification models for San Francisco, Great Valley, and Portland to Tualatin. We used new amplification models, construction and applied in the Atlantic and Gulf coastal plains to account for sediment thickness. We slightly revised this Western US attenuation boundary, which was used to apply the ERF and ground motion components. Regional and bias corrected global NGA subduction ground motion models for Alaska were used, and then we used 2 new Hawaii specific ground motion models. So a lot of things were updated. So now we get to the revision of the 50-state NSHM. Since the publication of the original model, several updates have been made based on feedback received from you, our users. We've revised the weighting and treatment of ground motion models near this Western US attenuation boundary. We've reverted weighting of gridded seismicity smoothing models in the CUS. We've updated the implementation of large megathrust earthquakes in Alaska. There's now the availability of full catalog seismicity rates in Hawaii for all periods and site classes. We made a few bug fixes, the model inputs and software codes, and now we've got high resolution grid data sets for CONUS at 0.05 degrees, Alaska at 0.1 degree, and Hawaii at 0.02 degree for all periods and site classes. So I'm just going to walk through those major updates that I just mentioned. The first one is the revised weighting and treatment of ground motion models near the CUS Western US attenuation boundary. Since the 1996 NSHM, the CUS Western attenuation boundary, shown here on the black line, has been used to separate the CUS from the Western US, and this separates both the ERF components and the ground motion components. Due to different tectonics, activity rates, rupture processes, and crustal properties between the CUS and Western US, where these two regions meet is complicated, as you probably all know, when it comes to calculating hazard, as this is not a strict boundary, but more of a transition zone. So in past NSHMs, we avoided a potential discontinuity between these two regions by summing the ground motion contributions from both the CUS and the Western US over a wide overlap zone. So this figure on the right shows the Western US on the left and the CUS on the right. The overlap zone goes from -100 to -115 longitude. And basically what we did is we let the smooth seismicity go over into this transition zone, and we then summed up ground motion models but didn't double count. This resulted in a smooth blending of hazard with no discontinuity between the CUS and Western US boundary. For the original 2023 50-state NSHM, we did two things. We revised the CUS attenuation boundary slightly based on new tomographic information and also by looking at ground motion models in the region. And then we also used this boundary as a strict boundary for ground motion models. And we also added in the -104-degree longitude boundary as a strict boundary for ERF. So on this figure on the right, you can see the -104-degree boundary and the updated attenuation boundary. So the issue with this is we now had some events, for example, in the old model, in this transition zone that were classified as CUS earthquakes. They're now being classified as Western US earthquakes. And before, when ground motions were being summed, we now have 100% of the ground motion being attributed to CUS ground motions. So this caused some issues that our users noticed. For the higher earthquake activity on the western side of the boundary, it was smoothed across into the lower seismicity areas on the eastern side of the boundary. And now that we're using that strict boundary for the ground motion models, 100% of the CUS ground motion models were being used on the east side instead of using that transition zone. This resulted in a sharp increase in hazard on the east side of the boundary, as you can see in polygon number 1 and 3. And there's also a few areas east of the boundary, number 2, that we can also see an issue that this caused. And again, this is due to the fact that the boundary is now a strict boundary, and anything to the east is getting 100% weighting on CUS ground motion models instead of Western US and CUS ground motion models being allowed to mix. And I just wanted to note that also with the addition of using 100% of the CUS ground motion models, as most of you know, when we look at the difference between CUS ground motion models and Western US ground motion models, especially at short periods and firmer rock sites, there's a big difference between the CUS ground motion model, the ground motion predicted versus the Western US. So here you can see a magnitude 7, 10-kilometer rupture for the CUS and then the Western US. So at short periods, there's a big difference between these two. And now that we're giving 100% weight to the CUS ground motion models, that's creating an even bigger difference. And there's also additional epistemic uncertainty and aleatory variability from the CUS models that are being counted for this. So to reduce this complex edge effect that we're seeing, we revised the original model to include a transition zone with a logic tree of ground motion models. Now we're back to using a transition zone in this area. So now we use the Western US ground motions get 2/3 weight, and the CUS ground motions get 1/3 weight in this transition zone from the boundary over to -104. The revised model still has some artifacts from earthquake rates being spread across the boundary to the east, but they are subdued compared to the original model, as you can see in the polygons 1, 2, and 3, as now less weight has been given to the CUS ground motion models that were causing that spike in hazard. So next, we're going to talk about the reverted weighting of gridded seismicity smoothing models in the CUS. On the right-hand side, I'm showing a plot of the difference in ratio models between the revised and the original model. And you can see some areas where we're going up in the red and down in the blue. For the original model, we applied weights of 0.4 to the fixed smoothing and 0.6 to the adaptive smoothing in the CUS. But then we found some examples, and one of these cases is an example case in Western Ohio, where there's 5 earthquakes between 1930 and 1944 with magnitudes between 3.9 and 4.6 that are closely located in the declustered catalogs. When we apply the adaptive smoothing methodology, these nearly correlated earthquakes cause a spike in hazard as it relies on the fourth nearest neighbor distance for smoothing. Until we understand how older and poorly located earthquakes may bias the adaptive smoothing, we decided to revert to the 2018 NSHM weights, where 60% weight was put on fixed smoothing and 40% was put on adaptive smoothing. For the Alaska subduction interface sources, which Peter will also talk a little bit more, consistent with the 2007 Alaska NSHM, the original 2023 Alaska NSHM models magnitude 7 to 8 ruptures on the subduction interface as floating ruptures along strike, with uniform rate considered by the graded seismicity model. By not floating the ruptures down dip, more earthquake rate is placed closer to the sites in south central Alaska, thereby overstating the earthquake rate in that region. For the revised Alaska NSHM, we adopted a distributed rupture model where the magnitude 7 to 8 interface ruptures are modeled as point sources using slab 2 gridded interface geometry, like the smaller magnitude 5 to 7 interface ruptures, but with a uniform rate. The largest magnitude 8 interface ruptures are still modeled as finite sources. For Hawaii, in the original model, the declustered catalog seismicity rates were used to calculate all periods and site classes on a 0.02 degree grid. For limited periods, specifically 0.2 and 1 second, and only one site condition, 760 meters per second, the full catalog seismicity rate was used to provide ground motion data as a sensitivity test, and we called this the research model, which is located on our science base. For the revised model, we now provide a data set that includes the full seismicity catalog for all periods and site classes on this 0.02 grid. This makes Hawaii consistent with what was done for CONUS and Alaska, which use the full catalog seismicity rates. This data set is being offered as an alternative option for users to consider. We had a few bug fixes, of course, that we needed to update. There were some bug fixes in the fault model input files that contained incorrect slip rates, geometries, or recurrence rates. So there's one fault in the Western US and a few in the Central and Eastern US that needed minor bug fixes. We also fixed an error in code that was calculating only half of the ruptures in the basin and range. So that caused some hazards to be missing. And then the implementation of the NGAE ground motion model bias correction, which we thought had been accounted for in the original version, was not. So we also included that. So now I'm just going to show some results that show some differences between the original model and the revised model. And I'm going to show PGA because the difference in ratios are very prominent for this ground motion intensity measure type. These are 2% and 50-year probability of exceedance ground motions. This is 760, so NEHRP site class BC, soft rock site condition. And I'm going to show some difference in ratio maps. The difference takes the revised model minus the original, and the ratio takes the revised divided by the original. So for CONUS, over here on the right-hand side on the top, we have the difference map, and on the bottom, we have the ratio map. And as we just talked about the changes that were made, we see hazard decreases between the CUS and Western US attenuation boundary. And this is due to our updated logic tree. So instead of having 100% weight on the CUS ground motion models, we now have 2/3, 1/3, with 1/3 weight being on the CUS ground motion models. So that's why hazard is going down, blue and green on these plots in this region. Hazard is increased in the basin and range due to that bug fix where it was missing some of the hazard from a focal mechanism. So we see Boise go up 13% and Wells, Nevada go up 25%. In the CEUS, the hazard has increased and decreased depending on where you are due to the changes of reverting back to the original smooth seismicity weights. So Western Ohio is now down 23%, and New York City is down 8%. The NGA East adjustment resulted in slightly lower hazard for short periods and slightly higher hazard for long periods, but that effect's being washed out with the overall hazard changes shown here. For Alaska, hazard decreased in the Alaska-Aleutian subduction zone due to better depth-dependent ruptures and the magnitude 7 to magnitude 8 floating ruptures. So on top, we have the difference map, and on the bottom, we have the ratio map. Anchorage ended up not changing, but Valdez, which is along the subduction zone, went down 10%. In Hawaii, here the change was that we are now using full seismicity rates instead of the declustered weights, and we don't see any hazard changes of more than 8% across the island chain. Hilo went up 4% and Honolulu went up 5%. And again, just to note that the original version of the model using the declustered rates is still valid. We're just now offering this revised version that offers the full catalog rates at all periods and site classes, just in case users want to consider this. So the revised model has been reviewed by a steering committee and recommended for publication by Earthquake Spectra. There's a discussion paper that will be coming soon. A new science base associated with the revised NSHM has been populated. So that's where you'll find the high resolution gridded data sets. And this will be available at the same time as the paper is published online at Earthquake Spectra. The science base associated with the original 50-state NSHM will remain available to users because it includes some data sets that have not changed. For example, the seismicity catalogs, and they do seismicity zones. And then, of course, as always, the source model and software codes are available publicly on GitLab. And the discussion paper will have a table with the tags used for each of those revised calculations so that users will be able to access that and reproduce the data if needed. And with that, thank you very much.
Great. Thank you, Allison. That's very helpful to see those recent updates, and very impressive, the scope of work in this project. So a reminder to the audience, we're going to hold the question and answer session for the end of the following all the presentations. Some of your questions you have now might be addressed by the coming presentations, but you're welcome to enter questions into the Q&A tab, not the chat, as things proceed. Okay, so moving along, we've got a full agenda here. Our next presentation is going to be by Ned Field, speaking about the earthquake rupture forecast underlying this model and kind of recent and potential future developments in this regard. So Ned, thanks for being here. Please take it away.
Great. Do you see my first slide?
Yes, looks great.
Great. Okay, well, thanks, Jack, and thanks everyone for joining us. I'm going to cover recent and future earthquake rupture forecast model developments, emphasizing future because Allison just covered a lot of what was done very well. As you know, there's two main modeling components used in hazard and risk analysis: earthquake rupture forecast and ground motion model. And just as the non-ergodic approach is a potential game changer on ground motion modeling, looking forward, we think that full time dependence, accounting for spatiotemporal clustering, is going to be the game changer on earthquake rupture forecast. And in fact, this is why we call it an earthquake rupture forecast, or one of the reasons, in that once you have fully time-dependent stochastic event set generation, it doesn't really make sense to call it a seismic source characterization. So that's a little background on why we call it an earthquake rupture forecast. The main future objectives are listed here, and I'm going to exemplify these throughout the talk based in part on what we did recently. But as I mentioned, fully time-dependent with spatiotemporal clustering. Improving epistemic uncertainty is going to be a perennial challenge. Risk-related valuation metrics and multi-cycle physics-based simulators. And these are both foundational and aspirational goals. We've done these things and relied on all these things already, but there's a lot more we need to do on each of them, and so there's big challenges ahead. You can find out more information on this in a forthcoming paper that's been, it's in press with BSSA, a scientific vision and roadmap for earthquake rupture forecast development. We say a USGS perspective because, we don't want to speak for the rest of the world. This is really how we see moving forward in the US. And what's shown here on the right, again, are the earthquake rupture forecast and ground motion model. And at the top just represents all the different information we need to grapple with in developing both of these system level models, from seismology, earthquake physics, tectonic geodesy, and earthquake geology. And the complexity here is the point. There is a lot of information we need to reckon with. And at the bottom just shows some of the different flagship products that rely on both these model components, not only the long-term NSHM, but also aftershock triggering or operational earthquake forecasting, risk estimates, and even scenario shake maps. So it's complicated, and the whole point of this paper shown on the left is to articulate everything that's being done in the context of earthquake rupture forecasts, with the goal of lowering the barrier of entry for, say, an early career scientist who wants to roll up their sleeves and help out. So that's the goal of this publication. Just a quick review of where we're at on earthquake rupture forecasts nationwide. We had the CONUS model published in 2023. Peter's going to talk about Alaska, that has also been published. Hawaii was published by Mark and others in 2021. Puerto Rico and U.S. Virgin Islands is in the process of being finished up, and there are plans in the works for the other U.S. territories that are inhabited. I also want to remind you that we have a 19-member participatory review panel. For example, they had a paper in BSSA alongside our CONUS overview, basically describing their review and their take on the model. And they also just recently delivered a report for PRVI. So this is a very important aspect of our model developments. Okay, so with respect to what's been done recently, as Allison said, a lot of faults were added and improved geologic slip rates. Deformation models are where we integrate GPS and improve upon those slip rates, and we have basically 5 different models that were developed for CONUS, for example. And these models are really complicated and take a lot of development. So we had some good progress on that. Basically have more multi-fault ruptures. We've improved the inversion approach to solving for these, as led by Kevin Milner. And we just think it's an objective, comprehensive in terms of uncertainties, reproducible and extensible framework for developing any fault-based earthquake rate model. And by extensible, we basically mean tell us what you don't like about our model, and you've given us a new constraint to add to the inversion. We had improvements in the off-fault gridded seismicity that was led by Andrea Lenos. And we also had a much broader range of epistemic uncertainties, which are integral to all parts of the model development. But the hazard implication evaluation was really led by Kevin Milner using OpenSHA. And by the way, I haven't listed all the associated papers with the CONUS model. There were well over 20 of them. But you can find those referenced in the overview paper. Interestingly, we included both multi-fault ruptures and wall-to-wall ruptures on the San Andreas, and found that they're not really that influential for individual site hazard curves, which are used in building codes. But you can also question, well, what about for other risk metrics, maybe portfolio risk? All you have to do is define your risk metric as damage in both LA and San Francisco to realize that these wall-to-wall ruptures become the entire question. And so there are other hazard and risk metrics for which various aspects of the model may be more important. And so one of our main future developments is these risk-related valuation metrics. We need to be looking at these things as we're developing the model so that we can broaden the potential uses of these models. Along those lines, as indicated in Mark's overview paper abstract, it's a long-term time-independent model that was released in 2023, defined for return periods greater than 475 years. in other words, it's really meant for time-independent individual site hazard curves. And again, really tailored for building code purposes. But we also know that our models are used in insurance and emergency management and other risk mitigation efforts. And so we want to make sure our models are appropriate for those purposes. This plot shows 100 years of monthly magnitude 2.5 and greater earthquake rates. And what's shown in red is a simulation that is realistic in terms of including spatiotemporal clustering in aftershocks. Shown in black is the exact same set of events, but their event times have been randomized over the catalog such that it turns it into a Poisson process. So our NSHMs basically approximate the red curve as the black curve. And the red curve is really a good proxy for the probability of triggering big earthquakes over time. And you can see that over a 50-year duration, half the time period shown here, the set of earthquakes from the red curve is about equal to the set of earthquakes for the black curve. In other words, a Poisson approximation in the hazard and risk calculations is probably good enough over a really long period of time. But at the same time, you can see that over shorter time periods, you can get a big spike in the rate or the probability of triggering big earthquakes, particularly following moderate or large earthquakes. And that's due to aftershocks or otherwise triggered events. And also notice that in other times when not much has happened, the fully time-dependent model is considerably below, maybe 20 to 50% below what you would get from a Poisson model. So this really tells us that, yeah, for 50-year building code, Poisson approximation is probably good enough. But for shorter time periods, you can have much bigger differences. And that's why we want to pursue these fully time-dependent models with spatiotemporal clustering. We have a prototype in California. It's called USURF3-TOS, basically integrated finite faults with elastic rebound and this epidemic type aftershock sequence spatiotemporal cluster model. And it really captures the rule of thumb that everyone should know by now, that every earthquake, large and small, has about a 10% chance of triggering something even bigger in the year that follows. And going forward, we really just hope to develop something like this nationwide so we can broaden the usability of our model. And to that end, these fully time-dependent models produce synthetic catalogs or stochastic event sets. And the good news there is that's what most of the commercial loss modeling companies already use. So the product handoff will be quite natural. We've also explored the potential implications of fully time-dependent red versus black time-independent. We have a paper in press at Earthquake Spectra that looks at this for California yearly risk estimates, average annual loss and losses that have a probability of being exceeded. And we basically conclude that, yeah, under circumstances that exist in user needs right now, the differences between black and red are definitely actionable. And so we think there's additional predictability that we need to be providing going forward. One thing we continue to insist, and Allison alluded to this, and I'm not going to go into it because it's kind of a can of worms, but there's a lot been published on it, and that is declustering the model before hazard or risk is really not advisable and not scientifically justified, which is why we don't do that anymore. Okay, few other long-term objectives. I mentioned improved epistemic uncertainty. More specifically, the deformation models, the slip rate estimates. We really have a small sample of the range of possibilities, and so we need to improve those epistemic uncertainties. Gridded seismicity still suffers from a sampling error. We only have one historic sample of earthquakes that we use to produce our gridded seismicity model, and we really need to consider what different historical samples would be telling us, and we need the full time dependent models to do that. There's also covariance among logic tree branches that may become more significant for portfolio analyses, for example. So we need to explore those. I already mentioned the risk-related valuation metrics, but I'll just assert that the best model for building codes is not necessarily the best model for shorter-term portfolio risk. And that's why we need to integrate the evaluation of a broader range of risk metrics during the model development process. And then finally, multi-cycle physics-based simulators. Really, we lack adequate data at the large magnitudes that drive hazard and risk to test a lot of the assumptions and attributes in our models. And these multi-cycle physics-based simulators really represent our best hope for making improvements along these lines. Again, you can read all about this in this forthcoming BSSA publication. And my last slide here is in that publication, you can read about some of our shorter term goals. And I'm not going to go through this list, but one thing I do want to point out is the second item, the long-term time-dependent earthquake rupture forecast that includes elastic rebound. We've been getting a lot of requests from commercial loss modelers to get this model out there. And I just wanted to say we're doing our best. We're a little bit distracted in the government right now, but this is our top priority in terms of the next earthquake rupture forecast model release. And all of these items, and I'm happy to field any questions later about any of these, will be implemented in our ongoing research model so that we're not trying to cram all this in at the very end of the next building code cycle. We can have a more relaxed handoff to the building code folks by implementing this stuff more continuously over time. So that's it. Thank you very much.
Great. Thank you, Ned.
You're
That's
welcome.
a lot to process, but exciting to see the future developments that are being pondered. Okay, so that's kind of a snapshot of what's going on in the seismic sources and the many ways of characterizing sources for these models. On the ground motion side, we now have a presentation from Morgan Moschetti, who's going to talk about the ground motion characterization in this model, as well as future plans in that regard. Morgan, thanks for being here, and look forward to hearing from you.
Yes, great. Thank you. And hopefully everyone can see this okay, and I'll go ahead and start.
Yeah, looks great.
So thanks to the organizers here for this opportunity to present on the overview. So I'll be focusing mostly on the updates on the ground motion side that we developed for the 2023 NSHM, and we'll very briefly touch on some of the future updates that we've started to implement in the Puerto Rico and U.S. Virgin Island NSHM model, and that we hope to advance for the 2029 50-state update. So this is obviously also a large group, and so I just want to give credit to everyone who's participated in the ground motion update for 2023. So in the next 15 minutes or so, I'll present on the following topics here. So first, I wanted to take a moment and just describe the update process on the ground motion side. I'll touch a little bit on the CUS boundary update, which, as we heard from Allison earlier, has been updated in this revision. And then the focus of this presentation will be on CONUS or conterminous US. And so I'll touch on ground motion modeling approaches in the Western US for shallow crustal earthquakes, Central and Eastern US, and then also Cascadia, with highlights mostly on the new material, but also some brief overview of some of the various modeling approaches that we have there. So as the NSHM project has done since '96, the update process always involves a number of public workshops. That was true again for 2023. We had a set of workshops that were ground motion focused, and many of you attended, and those are a great opportunity to present your early feedback and for us to start to present initial models, and that was no different. And so we touched on a number of topics in these workshops. What was new for 2023 was that the NSHM project stood up a ground motion review panel. This is separate from the steering committee that gives us feedback on the entire NSHM model. This was just a ground motion focused group. This was led by John Stewart and included experts really in ground motion, seismic hazard, and risk modeling that gave us feedback on this topic, provided us a summary report here. And this is something that we hope to continue forward in the future in a modified way to become more participatory. So this is an ongoing group. Finally, in terms of documentation, there were also a number of reports or articles that came out of this update. All of these were published in Earthquake Spectra, and so you can look to the overview paper for all of the various references on these topics, but there's certainly a lot of detail in each of these papers that can be gained. So the 2023 update, as we heard, included a pretty significant revision for the CUS Western US boundary. This boundary had originally been developed in 1996 by Frankel et al. And this is important for the ground motions because it determines which GMMs we select for crustal earthquakes. So specifically whether we're using the Western US suite of GMMs or Central and Eastern US suite of GMMs. As we heard from Allison, some of the interaction between the ERF and GMM complicated this implementation. And so there's been a revision in this treatment that now includes this merging of GMMs. And so the descriptions of this are in the Peterson et al. Documentation. And so this is an important update, but one that we still need to consider as we move forward, which is the appropriate treatment as we transition from Western US to Central and Eastern US for ground motion modeling. Okay, so starting off with the Western US GMMs, I'll have a similar slide for each of the three regions, and this is a figure that's taken from our overview paper. In the Western US, we used the same multi-model approach that was used in 2018. It's this combination of GMMs from the NGA West 2 project, and then the figure here shows that some of the updates that were done as compared with what was used in 2018. So areas in red are what we revised for the 2023 update. The other areas were just carried forward from our approach that was used in 2018. So 2018, we used the VS30 scaling models that were provided by each of the GMMs. That was used again. It was discussed whether or not we should introduce VS30 scaling models, independent VS30 scaling models that came out of the NGA subduction project in Cascadia. This was something that we were not able to implement for 2023, but could be considered in the future. In 2023, we did consider the treatment of shallower parts of deep basins and the treatment of areas that are located outside of basins. And so I'll highlight that in a slide later. So that was applied in two areas, San Francisco Bay Area and the LA region. The basin depth scaling models had a modified treatment. In the LA region, we introduced a simulation-based alternative model for basin amplification from the SCEC CyberShake project. We retained the empirical GMM models that were introduced in 2018. The basin depth models for the Western US were maintained, except for the introduction of some new basin models that I'll describe later. And we also retained the treatment of additional epistemic uncertainty, which is described in this Razan et al. Documentation, and the same treatment for aleatory variability. So 2023, we evaluated several new regions for introducing new sedimentary basins, which are known to have an important effect on long period ground motions. The figure on the left highlights the areas where existing models for basin effects were included in 2018. Those are shown in blue, and then the areas in red show the regions that were considered for introduction in 2023. So for two of these regions, Portland and the Great Valley, we developed basin models based on various approaches, geologic information, seismic velocity models, et cetera, as described in the Adi et al. Paper. For the Reno Sparks Basin or Reno Truckee Meadows Basin, this was provided by an external collaborator. And in all of these cases, we evaluated whether the existing basin amplification models from NGA West 2 were appropriate. So we collected ground motion data and evaluated the amplifications that were observed in that data with the existing NGA West 2 models. In two of the cases, we accepted the models for use with existing NGA West 2. And so for Portland and the Great Valley, we ultimately decided to use those geometries in our 2023 NSHM. And the effects are shown on the right here. So at long periods, we get increased ground motions, preferentially where we have deeper parts of the basin. So in the Great Valley, that's in the western parts of the basin. Here, Portland Tualatin Basin show differential effects due to the depths of those two basins in the Portland area. As I mentioned, in the Western US, we also introduced an alternative basin amplification model from the simulations. This has been a goal for a number of years since the development of these suite of 3D simulations by SCEC, the CyberShake project that simulated millions of seismograms using 3D seismic velocity model for Southern California. So the piece that we decided to extract there was just related to the basin amplification effects. And we developed models, essentially alternative ergodic models that could be used with the NGA West 2 GMMs as alternative models. The effects are shown here, or examples are shown here for 1 and 5 seconds. So these are effects that are limited only to long periods, because those are that's the period band for which the deterministic calculations for CyberShake are appropriate and provide an important alternative model for what may be expected in future events in Southern California. Following up on the implementation of basin effects in 2018, we returned to the treatment of ground motions in areas where we have shallower sediments. So this is effectively the area where we have relative de-amplification. So this delta Z1 is less than 0. In 2018, we only allowed for amplification of the deeper parts of the basin using this and other constraints, but this was reconsidered in 2023 based on feedback about the importance of understanding the effects of shallower sediments on ground motions. And so this really required focus on both ensuring that the ground motion data was consistent with these model predictions in areas with shallower sediments, and also that we were limiting this application to areas where we have high confidence in seismic velocity models. And so in doing that, we've modified the region over which we state that we have high confidence in seismic velocity models. So the dashed line is showing the region that was published for 2018. The solid line is the region for 2023. And you see that in San Francisco Bay Area and LA, these regions have differing effects, and that we expand the region for San Francisco Bay Area based on reevaluation there, and constrict the area for Southern California. Moving to the central and eastern US, we carried forward the two basic branches of the logic tree for the ground motion models. One, which is given by the NGA East logic tree, which was significant effort for modeling central and eastern U.S. ground motions. The other being the USGS multi-model approach with these updated seed models, and of which there were 14. What we did consider, though, was an adjustment to this that I'll describe in a moment. The site response models, or VS30 scaling models, are carried forward from what was introduced in 2018. It's described in a couple of papers. We introduced a deep sediment amplification model for the Atlantic and Gulf coastal plains, and finally carried forward the same aleatory variability models that were used in 2018. So an important modification for the central and eastern U.S. was the recognition that there was this need for a data adjustment, and that's shown here on the bottom right. The solid line is showing the bias. This is in natural log units of observations in the central and eastern U.S. relative to the ground motion predictions. And so at short periods, and this is 0.1 second here, the maximum here is at around 3 or 4 seconds. We were seeing this over prediction at short period and under prediction at longer periods. This was facilitated by an enhanced ground motion data set that was led by Ramos, Sepulveda et al. And this analysis. And so we wanted to introduce some corrections as a potential for ground motion modeling. And so as a new logic tree branch in the GMM logic tree, we allow for these adjustments to be introduced to both of the ground motion suites of ground motion models. There's some work by Ramos, Sepulveda et al. To explain the cause of these data adjustments, and they can explain most of this due to differences in the site amplification model that were used in the development of NGA East, which are primarily from Western U.S. data sets compared to the CUS specific site amplification models that are now used. So this was introduced at partial weight. The effect of this adjustment, which again was just used at partial weight, is this reduction in ground motions at short periods across the region, and this increase in ground motions at long periods across the region. As I mentioned, for the first time in the CUS, we've introduced effects for from deep sediments, and so this is in the Atlantic and Gulf coastal plains. This was a compilation of deep sediment information by Oliver Boyd, and then the use of amplification model that was developed externally and implemented here. The effects are shown here, and so again we get short period de-amplification that scales with basin sediment thickness, and long period amplification that again scales with sediment thickness. Finally, for the subduction zones, we had really a wholesale update of the logic trees that are used in these areas based on the availability of the NGA subduction GMMs. In both of the cases, so for interface and slab or intraslab earthquakes, we used the new NGA subduction GMMs, specifically only using the Cascadia version of these GMMs. We also combined the GMMs with some of the GMMs that had been used in previous updates, so the ZAL-06 model and AM09 for interface, and ZAL-06 for the intraslab. This was done because of an observation that there was this pinching in the NGA subduction GMMs, and we didn't want to underestimate epistemic uncertainty. So I will just highlight that the NGA subduction effort was really significant in the sense that it allowed for regionalization of VS30, regionalized basin depth scaling models, and path attenuation terms. The effects of the introduction of these new GMMs were important in a number of areas. So at short periods, we see higher ground motions at the coast. Also in the Puget lowlands, that's contributed both by differences in the median aleatory variability and intraslab earthquakes primarily. At longer periods, we are seeing reduced effects, mostly from distance attenuation, although that higher aleatory variability is important again for future lowlands. This area also, we introduced a basin amplification model from the M9 project that's described in these papers here. In total, we see a number of widespread changes across the region. These are maps at 0.2 seconds and 1 second, showing some of the combined effects of the GMC update. And this is in the Peterson et al. Overview paper. And since I'm out of time, I'll just quickly mention that we're moving forward on a number of different areas in the GMC space, including introduction of scaled backbone models, the availability of hazard fractals, which has really been enabled by Kevin Milner and the hazard group, is going to allow new evaluation of the GMC, and finally these regionalized aleatory variability models. So I'll pause there given the time, but happy to answer any questions later.
Great. Thank you, Morgan. Okay, our final speaker of the session is going to be Peter Powers, speaking about the Alaska seismic hazard model. It's been an important one given the large spatial extent and the long time since the last update, so some special treatment here is merited. Peter, thanks for being here, and I look forward to hearing what you have to say.
Thank you, Jack. Can you hear me?
Yep, sounds great. Looks great.
Okay, great. Thank you, everyone. Thank you, EERI, for sponsoring this webinar. I want to spend a little time talking about the 2023 update for the Alaska part of this 50-state update and highlighting some hazard and changes. You can see here this map on the right. We've got a lot of hazard concentrated in South Central Alaska. And compared to the 2007 model, it's been quite some time since the Alaska model has been updated. We're seeing some pretty large increases in hazard as a result of adoption of the new model features and ingredients. As I said, the Alaska model was part of the 50-state update and is published here as part of the special collection on earthquake spectra, and you can read more about it there. And I'll be giving just a very high-level overview today and really trying to focus on the key issues that were giving us and others concern regarding the high increases in hazard in South Central Alaska. These are ratio and difference maps just for 0.2 second spectral acceleration of the soft rock site class. On the left, you've got differences between the 2007 and the 2023 model, and then ratios on the right. But what you can see is that in South Central Alaska, you've got increases up on the order of about 1G over and above what was forecast by the 2007 model. And so we really want to understand what has given rise to that. Broadly speaking, what went into the Alaska model were new fault and interface sections. So we further refined the subduction interface model. Many new faults were added to the crustal fault model. Formerly in the 2007 model, you really only had the Denali fault and one or two faults down along the coast and the Queen Charlotte Fairweather system. All these colored lines represent effectively new additions to the model. New methodologies were adopted for developing the gridded seismicity models, consistent with what we're doing now in our NSHM process, where we are leveraging the slab 2 subduction interface models and codes related to development of that slab 2 model to segregate our earthquake catalogs and improve the catalog processing for the gridded seismicity models. We've introduced new ground motion models. We use NGA West 2. Those are fairly well-established ground motion models for the crustal faults within the Alaska model. And then I'd also adopted the NGA subduction ground motion models for use with the subduction interface. This model was reviewed and approved by the Alaska NSHM Scientific Review Panel, as well as the NSHMP Steering Committee. We had some additional review of the ground motion models conducted by a Tiger team that we assembled to address concerns related to the large increases in hazard late in the model development process. And here's a link to the Spectra paper itself. The key impacts, and using Anchorage as sort of the standard bearer for South Central Alaska site, interface and intraslab rate model increases. So there's been an increase in the modeled rates of interface and intraslab events. More gridded seismicity rate is associated with the subduction GMMs, and gridded seismicity rate is physically and more correctly modeled as being closer to the site. And I will show you more about that in a subsequent slide. The ground motion models broadly exhibit increases in medians and sigmas relative to their 2007 counterparts. We had an addition of a Prince William Sound zone source in South Central Alaska, and the use of total catalog rates for gridded seismicity, as was mentioned by Allison and Ned, have slightly increased rates based on gridded seismicity across the model. So let's focus on the intraslab and interface gridded source models. On the left, we've got a summary of what was included in the 2007 model. The catalog, the earthquake catalog, in the 2007 model would have been divided up into depth slices and then smoothed and then modeled at a uniform depth. And so in the lower cross section, schematic cross section across the subduction zone interface, in 2007, you would have effectively had intraslab sources modeled along these two dashed red lines. For 2023, we adopted the catalog segregation algorithm that's used to, in a probabilistic sense, divide an earthquake catalog into its interface, intraslab, and crustal earthquake components. This is the first step that is used in developing the slab to interface models that allows them to identify and isolate the interface and intraslab sources that then can be used to define the geometry. Furthermore, we then use that geometry to model the depths of the intraslab and interface sources. And effectively what this does is, in certain locations across South Central Alaska, can bring some of that earthquake rate actually closer to the surface and closer to sites like Anchorage. Something that's interesting to look at in the case of Anchorage, the hazard change is pretty significant, and it's about a twofold increase over the 2007 NSHM, with 0.2 second spectral acceleration values peaking at about 3.45 G. For reference, on the right here is a uniform hazard response spectra plot, just showing you for context, the black line is Anchorage. And so while it is much higher than many other sites across the western US, you will note that the ground motions predicted by this model are significantly lower than those predicted for the large magnitude earthquakes that dominate hazard in the central part of the central and eastern US in the vicinity of the New Madrid seismic zone. Disaggregation of hazard highlights some of the model differences and changes between 2007 and 2023. What you can see here in the lower plot, disaggregations, for those of you not familiar with it, pull apart the hazard and allow us to visualize it in terms of what's contributing to hazard at different distance and magnitude bins. So you've got magnitude on the one horizontal axis and distance in the other horizontal axis. In 2007, this single column right here represents the only earthquakes that were considered large magnitude finite earthquakes, finite ruptures that would have occurred on the subduction zone. And we believe that that's a sort of doesn't represent a complete model of all possible earthquakes that could occur on the subduction interface. What you see here in the disaggregation for the 2023 model is a much more uniform distribution of contributions to hazard from ruptures at shorter distances that then taper with distance. And then this population at the higher magnitudes here represents the broader population of interface events that are considered in this 2023 update. This is the same slide as before, but with some updated plots. The disaggregations we were looking at before are total disaggregations across all source types in the top row, and then just interface that I was highlighting before in this middle row with the single magnitude 9 event that was basically a representation of the Great Alaskan Earthquake, and that's all that was then considered in that 2007 model. On the bottom row, we have interface and intraslab gridded seismicity. And what you can see in 2007 is that these two populations at different distances, this further distance represents that population of intraslab events that was modeled as a uniform depth slice of sources and ruptures. And we don't believe that's fairly realistic relative to what we know or what we are able to do when it comes to defining the subduction interface geometry. And so on the right, you see a more uniformly decreasing level of contributions from the intraslab and interface smaller magnitude events. In summary, this plot on the left is magnitude frequency distributions for all earthquakes within about 200 kilometers of anchorage. The black dashed line is the sum from the 2007 model, wherein we had a magnitude 7 or greater earthquake about every 20 years. In this updated 2023 model, we forecast magnitude 7 in the vicinity of Anchorage probably about once every 10 years or so. But that can still be at quite some distance from Anchorage itself. Now, one of the biggest issues that came up was, well, how are the ground motion models behaving? NGA subduction at the time of development of this model was very new. Unlike NGA West 2 ground motion models, they've not been adopted in NSHMs globally. Only now are they being adopted. And so they really hadn't been scrutinized in a way that the NGA West 2 models had. So the issue is the Alaska NSHM update implies high ground motions for subduction sources. Are the NGA sub ground motion models credible? Are the Alaska interface models? So in developing NGA subduction, a suite of global models were developed, but also regionalized models were developed. And so at first, we really focused in on the Alaska regionalized model. Turns out, though, in the case of subduction interface, the Alaska regionalized models are really based on limited data. So it's moderate magnitude earthquakes at really large distances, and those ground motions are being extrapolated to the largest magnitudes. And we really didn't have confidence necessarily in the just not the NGA subduction process, but just the amount of data that had been available at the time of the assembly of the NGA subduction database. So we assembled a Tiger team of those people listed here, and their conclusion was to use the Alaska regionalized intraslab GMMs as published, as there was abundant reference information in the NGA sub database that gave the panelists confidence that those models were adequate for use in an intraslab environment. However, for subduction interface ground motion models, they recommended that we use the global interface GMMs instead of the regionalized models, and that we apply a bias correction that includes data that had been gathered since the completion of development of the NGA subduction database. Most importantly, the 2021 magnitude 8.2 Chignik event, which, while not co-located with Anchorage in South Central Alaska, provided, though, a reference point for a larger magnitude interface event that was still sort of within striking distance of Anchorage. And so we included additional data and as adjustments to the global models. Those adjustments are shown here in this slide. In the panels on the right, this is if we just consider new events only, events that were not in the NGA subduction database, and you can see that there is an overprediction at short magnitudes. So negative numbers is the models are overpredicting ground motion. Positive numbers is underprediction at long periods. Ultimately, the panelists recommended that we use the NGA sub database values plus the new events to provide the bias correction, at which point you get slight overpredictions at long periods and larger overpredictions at short periods, which then bring the ground motions down relative to their published values. This was an interesting test too we applied based on the panel's recommendations for 2% and 50-year hazard. What we're showing here are hazard curves at spectral acceleration of 0.2 seconds in a soft rock site class. The red and blue lines are the 2007 model, two different versions of the 2007 model, but you can see that they're fairly close. The recommendation was, well, let's look at BC Hydro, which is a well-accepted and widely adopted ground motion model for subduction interface. And in point of fact, when you put in BC Hydro, which produces larger median ground motions than the ground motion models used in 2007, as well as much larger aleatory variability, the slope of the hazard curve decreases significantly and yields much larger ground motions. That's just using the 2007 earthquake rupture forecast. Now with the 2023 earthquake rupture forecast, in the panel on the right, the yellow line that was on the left is now the blue line on the right. Then what we see are these other curves, which are variants of the 2023 model, either using BC Hydro or using the NGA subground motion models, and you can see a commensurate additional increase as a result of increases in the rate component of the earthquake rupture forecast. So the takeaway is that there are significant changes in the Alaska model. They stem largely from adoption of new ground motion models, but also the inclusion of what we believe to be significant improvements to the earthquake rupture forecast. I will close with a final slide here with a plug for the USGS Earthquake Hazard Toolbox, which I know many attendees are probably users of. As mentioned, and I think we'll probably get into this in the Q&A, all of this, the 2023 model, plus any new development that we're doing, is rapidly making its way into the Earthquake Hazard Toolbox. You should have access to the 2023 model. We commonly compute large static data sets that get used and feed into building codes. Those too will be made available pretty soon within the hazard tool. And so I will leave it at that and hope to increase our time for questions. Thank you, Jack, and thank you, EERI.
Great. Thanks a lot, Peter. Very helpful. Maybe while that screen is still up, I'll note, as an independent user of this earthquake hazard toolbox, I've used it in my class at Stanford. It's really phenomenal. It really very easy to navigate. The students have really found it quick to kind of get in and find the information they want and ask kind of probing questions to understand features of the model. So highly encourage people to check that out and utilize it. Okay, so that's the end of our presentations, and we've got the remaining time for some question and answer with the speakers. If the speakers could turn their cameras back on, I'll comb the Q&A box and direct a few questions to them. If you've got remaining questions, you can still add them to the queue as well. Let's see. I guess there's a few questions that have been answered in writing on the Q&A box. The participants live can see those, but just to make sure the webinar viewers get some detail. Maybe one I'll start with was there was a question about the BSSC NEHRP provisions in the ASCE 7 standard that relies on the USGS models and how that relates to this revised model that Allison presented. So I guess for the record, that the revised model is the model being adopted by the code committees. I think next week's webinar will discuss that in more detail as well. Allison, I don't know if there's any more you want to say with regard to that.
Nope, just that you're correct. The revised model is the one that's currently being considered for both NEHRP and ASCE 7.
Great, yeah. And Earthquake Spectra will shortly add this new discussion paper to the special collection so that those updates are all documented in writing in an archival form as well. Great, okay. So moving to some other questions, maybe one, since Peter had just displayed that the web tool for the hazard model updates. There was a question in here as well about OpenSHA, which is another product that the USGS is producing to document hazard calculations and things like that, and whether the OpenSHA models are kind of compatible or how they relate to the web tool and the other data releases produced by the model. Ned, I don't know, could you say anything about that?
Yeah, sure. So OpenSHA was used for doing the inversion-based fault system solutions and also for the epistemic uncertainty calculations for the Western US analysis. And now it's being used for Puerto Rico for all the ERF development and all the epistemic uncertainty analysis. Our goal is to, we're still in the process of comparing exactly what the two codes produce and going through a verification process. In fact, that's the primary delay in putting out a long-term time-dependent model, because that'll be an OpenSHA, and we don't want to put that out until we know we can match Peter's mean hazard maps as well. Peter, you want to add to that?
No, I think you've summarized it well enough. They're very close. We're just refining things, and anybody who's done any PSHA work knows there are just cascading numbers of decisions that get made and how you implement things. And so I anticipate by calendar year end there'll be much tighter reflection and duplication between the two codes.
Great, thank you. We had a couple questions about return periods of the hazard results. Some questions about kind of the range of return periods that the models were scrutinized under, or when they're under which they're determined to be reliable. as well as what you think about for people trying to assess hazard at more frequent return periods for smaller earthquakes. It's kind of a broad question. I don't know if any of you have thoughts on what you can say there.
Are you getting into the full time dependence implications, or when you say return period?
Maybe I should have filled in one more detail, and I can ask a leading question a little bit. I believe that the documentation in the review talks about kind of assessment for of hazard results for return periods of 475 years, 2,000 years, so on. Could you comment on kind of the range of return periods of the hazard results, not necessarily the source
Yeah,
model?
I think the right way to put that is we're pretty confident that for any hazard or risk metric that is greater than about 500-year return period, or a 1 in 500 chance of occurring in a given year, you can use the Poisson version of a fully time dependent process with a lot of confidence. Now, there may be some pathological cases where that's not true that we haven't yet explored. When you get to shorter time periods, say yearly, if you're trying to set yearly insurance rates or something like that, then the differences can be more important. That doesn't mean that the Poisson version of the NSHM isn't still best available science. It just means user beware that you might want to further explore the applicability of these models, because we haven't had the chance yet to do anything outside of California. And in California, just some of the more primary risk metrics that are typically used. So the wording in the reports tends to be a little stronger than I would say. I wouldn't say you can never use this for less than 475 years. It just means user beware. You might want to consider the consequences of doing so. And by the way, for hazard and risk metrics that are the probability of one or more exceedance, you have a somewhat counterintuitive result in that the Poisson version implies a higher hazard or risk than the fully time-dependent model, mostly because Poisson doesn't have the quiet periods and more active periods where you get multiple exceedances. Well, the one or more exceedance doesn't really count against that. So this is a longer term issue that we're going to have to get together as a community and talk this through, because those of us doing these calculations are just kind of discovering things. And it really comes down to, it depends on exactly what your hazard or risk metric is. But I don't think you're doing anything horrible if you use a Poisson version of a fully time dependent as your first estimate.
Great, thanks. There's a couple questions as well that came in about this smoothing, treatment of smoothing of the ground motions across this western U.S. to the central eastern U.S. Boundary. Kind of one question about kind of why are there differential impacts at the Wasatch Front versus out into Nevada. Another one asking about kind of what's done on the eastern side of the transition and if that's was considered and how important it is. So I don't know if that's Alice or Morgan perhaps could comment on it.
Can I start with that?
Oh, sure.
Yeah, I think they're both Jim's questions, and one's about what was missing in broadly across the basin and range was we tend to model gridded seismicity using a distribution of focal mechanisms. And for one reason or another, the normal component was being ignored. So there was an underrepresentation of earthquake rate in the gridded seismicity model, and that's been fixed. That model, however, as you get to the Wasatch Front, the gridded seismicity model is completely overwhelmed by activity on the faults of the Wasatch system itself. And so you don't really see that increase. And now you're into the area where these adjustments to the ground motion models are also overshadowing that modest increase that resulted from that bug fix. In addition, where there was that error, the border for that region where normal faults are considered ends right around the Wasatch Front, perhaps, I think, aligned with the attenuation zone. Then the second question was to the
towards the east of the transition.
To the east. Oh, and implementing a spatial taper of use of the ground motion models. It's unfortunate the prior models and the difficulties we had with them, we effectively encoded tapering and blending of the ground motion models by virtue of tapering and blending the gridded seismicity part of the earthquake rupture forecast. With the switch to using the inversion methodology and having a regional magnitude frequency distribution constraint, we moved to splitting the Western US and Central and Eastern US along this 104 boundary. Now, these side effects that occurred by using the attenuation boundary as a hard boundary between two different populations of ground motion models, it became clear not till later in the model development process the impact that that was going to have. And that's what Mark's paper is really trying to address. And while it's not ideal, and I think in a future update to the CONUS model, we will go back and give more thought to how to apportion or divide up the country for development of the gridded seismicity model and then subsequent integration with the inversion methodology. We can't do that in this time frame. And so the fix that we came up with was to to adjust the logic tree of ground motion models to blend CUS and Western US components, and we believe that was an adequate fix for at this moment in time.
Great. Maybe another question dealing with boundaries in a different way. There's a question about kind of the northern and southern edge of borders of the central eastern US. And has there been any communication with our neighboring countries or kind of thinking about edge effects in hazard calculations?
But yes, we've had ongoing discussions, at least with Canadian. I mean, Peter, you've been involved in this, so you can probably speak to it better. And we've had some initial discussions with folks in Mexico to ensure it's an ongoing issue, right? To assess these NSHMs across countries and developers and ensure that you're getting consistent results. And hopefully, I think the production of epistemic uncertainty will really also facilitate that so that we're not looking at, minor differences in mean hazard that may be due to choices in your logic tree and weightings, but that you have really consistency between the full hazard models.
I would also then follow on that one, just saying that, we typically in our own workshops and in these type of webinars, we really focus on earthquake rupture forecasts and ground motion models as being like the drivers of change, but there's the implementation side of it too, and the decisions you make about how to take that information and develop those 3D models of faults and simulate ruptures and parameterize those ruptures so that you can feed them into the ground motion models. And Canada does things so differently than we do that you really have to come to resolution on okay, well, how are we going to take the available data and integrate it in a way that produces more uniform hazard across the borders. Both approaches are defensible, both Canadians and ours, but they are very different. And so that naturally leads to differences in hazard.
Yeah, and we're talking about differences in mean hazard when we should really be quantifying the full epistemic uncertainties. And the question is, how much do they agree given the uncertainties? And if they don't, then we have some explaining to do.
Great. Let's see, there's a question to Morgan probably. Interest in the status and ongoing efforts regarding the non-ergodic ground motion model.
Oh yeah, I saw that. Right. So
about that or what you've got planned?
Well, right. So we haven't set plans for the 2029 update. We're certainly thinking about it, and I guess I can comment on a few things that are being considered. One is certainly looking to NGA West 3 as they move forward and start to produce models to see honestly what level of non-ergodic models are available from the developers. Internally, there's consensus that if we were to be introducing this, or the first introduction of non-ergodic components would really just be partially non-ergodic, so just the spatially varying side effects that would most likely be our first introduction. There are some complications with delivering that type of model to engineering users, given the choice that NSHM has made in the way that we compute hazard for uniform VS30. And so we need to think through that and really discuss with other users what the value is of that. There's been a pretty significant effort internally at the USGS to develop ground motion data sets that would enable US-wide calculation of non-ergodic adjustments. But again, looking towards NGA West 3 and other GMM developers to get input on the techniques for doing that. And finally, I'll just say that, one consideration is also just moving to a non-ergodic framework for the hazard calculation, which could at least move us in that direction and allow for the adjustments. It would also ensure that any epistemic uncertainty didn't cause some kind of jump as we look at variations between future updates. So that's just a few of the directions that we're considering with respect to non-ergodic.
Great. Let's see, maybe back to the earthquake rupture forecasting side. Ned, you talked a bit about the declustering and the consideration of aftershocks being treated differently. The question is, can you elaborate on how declustering programs are or are not used in the 2023 update?
Yeah, sure. So we continue to rely on declustering algorithms when building the model. For example, one of the things we want to do is take the historical seismicity and instrumental seismicity and estimate the long-term rate of events at each point in space. And to do that, we obviously have to remove aftershocks. Otherwise, we'd have inflated rates just where we've had events and bias low rates elsewhere. So the declustering is still an integral part of the model development process. The problem is that our best declustering model, and it's not even perfect, but the best declustering model takes out half of all earthquakes at all magnitudes. And that really provides the best estimate of the long-term rates. So when it comes to doing hazard or risk modeling, you don't want to take out half of all earthquakes. That's removing half of your hazard or risk. And so in the past, we did no harm because the declustering algorithm, effectively, it's called Gardner-Knopf, 50 years old now. It only took out little earthquakes. But again, a more modern, best available science declustering algorithm just takes out way too many earthquakes to justify applying that in a hazard or risk calculation. And it was also done in the past so that you could be warranted assuming a Poisson process in the hazard or risk calculations. But you're better off just including all the earthquakes and treating it as that black line I showed rather than the red line, than to try to monkey around with any declustering for the purpose of hazard or risk. But we still use it in building the model.
Great, thank you. All right, so we're just a couple minutes short of 90 minutes with the scheduled time here. So I suspect some of our audience members are going to need to peel off for other commitments. Probably most of you online can't see, but we've actually had almost 200 people or a little over 200 people on the call for the last 90 minutes. So I think that's a tremendous sign of the level of interest in these important models and appreciation for all this work that's been done. I think it's also quite remarkable to sit here 90 minutes in to see how much information these four speakers have been able to convey, as well as this very kind of high-level technical discussion of some of these model details and implications. So quite appreciative of the speakers as well as the very thoughtful questions from the audience today. We've been chatting offline. Some of the speakers are willing to stay a few more minutes to answer a few more questions, so we may continue here a little bit informally if there's some other detailed questions people want answered, including a few that are remaining in the queue. But I know that many of you will probably be logging off in the next minute or so. So we just wanted to thank you all for your appreciation and offer a formal thanks to these excellent speakers while everybody's still here. Elizabeth, you want to take it from here or share anything else?
Yeah, I'll take over. Since we have our speakers have kindly agreed to stay on a little bit longer. Excuse me, I know Jack has to step off. But I think we have a couple questions about the use of physics-based hazard modeling in the seismic hazard model. One, I believe, excuse me, Morgan has answered already in writing. But if any of the speakers would like to comment on that, that would be great.
Yeah, well, I can just summarize what I wrote, at least on the ground motion side. Certainly, direct use of the results from 3D ground motion simulations is a goal for the ground motion characterization. We don't think they're ready yet, and that's a view I think that's generally held across the hazard community. But the approach to getting there and starting to introduce more features from the simulations is to modify our approach, which is also consistent with others, is to modify existing GMMs, so the empirical GMMs, for example, with different features from the simulations until we have confidence in those simulations. And so for 2023, we modified the basin effects for two different regions in LA and the Seattle basin. Yeah, we could imagine modifying the absolute amplitudes, looking at the variability that comes out of simulations, a number of things as we move towards introduction as a branch in the logic trees.
Great. And then we have a couple questions about regional impacts of changes to the model. One about New York specifically, and the significant increases in spectral acceleration, and one about the changes that will likely increase ground motions for the Pacific Northwest, and about how agencies might respond to that forecast. So any comments on those?
I think I just answered the New York City one in the chat. But yes, the hazard at New York City is dominated by the gridded seismicity model. So it's a mixture of the weight changes, but also the other things involved in the seismicity model. So any updates to the catalogs or the declustering models also have caused some of the changes between 2023 and 2018.
Great. And anything on the Pacific Northwest question? I will note that the webinar next week following up, we'll talk a bit more about engineering and building code impacts. So I think that might also be addressed somewhat there. But the question was partly about what those decisions mean for how other agencies, municipal, state, otherwise might respond to this model.
Not sure if I still see that one. Did someone else, any of the other speakers answer that? And I just missed it.
What was it again? Pacific Northwest?
The Pacific Northwest hazard is highly sensitive to the time-dependent introduction of time-dependent models.
I think I remember seeing that come up. And I'll just echo, I think sort of what Ned said at one point, that our development of a time-dependent model does not in any way assume or guarantee that that would make its way into building codes. I think we would be producing at that point multiple models for multiple applications. Is that a safe statement, Ned?
Yeah, I would agree with that.
Great.
One could imagine at some point, 20 years down the line, the two may be the same, but I think we may end up with a different model for short-term hazard and risk analysis that is fully time-dependent stochastic event set based. But we would also continue to develop the long-term building code model as well.
Great. And then finally, I see a question about the vertical components of motion in the model.
This has come up. It's on the master list of things to do, but we've not yet turned our attention or focus towards developing vertical components of ground motion. Historically, ground motion model developers would sometimes publish tables of coefficients applicable to the horizontal and the vertical component. My guess is that we would move forward using H/V ratio models or something similar to convert the horizontal ground motions to their vertical counterparts.
Great. And then very last question about when the revised model results will be released. I think this is referring to the paper that's under review, but Allison, if you want to take that.
I'd say maybe a couple of months. Like I mentioned, the paper's been accepted. The only thing that we're doing is calculating the higher resolution grids. So those are populated on our science base. And as soon as that's done, the paper will be approved by USGS, and then it will just be up to however long it takes to be published in the journal. So I would say maybe 2 to 3 months, if I had to guess.
Great, and that will be added to that same special collection page that was linked at which you'll also be able to find by going to the Earthquake Spectra Journal page. So once it's there. All right, thank you again to our speakers for these excellent presentations and for taking time to respond to all these questions. Thanks again to all of those who joined us today. I just want to briefly mention that you'll see a survey pop up in the Zoom window when this ends, and you'll also receive a link to that via email tomorrow. And we'd appreciate your feedback. That helps us improve our webinar and other educational programs. You can learn more about EERI at our website, and if you're not a member, we very much encourage you to join us. If you want to support our reconnaissance work and our other programs, you can also donate to the LFE endowment. And then finally, once again, I just want to thank and acknowledge our funders, FEMA, that endowment fund, and EERI members like many of you. And I hope to see you all next week for the follow-up webinar in this series.
Good, thanks.
Thank you.
Thanks a lot. Bye.